Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Oil whirl. In some lightly loaded, plain journal bearings, a phenomenon called oil whirl can occur. This is caused when the rotating unit pushes up an oil wedge in front of the shaft. As the shaft tries to roll over the oil wedge, the shaft whirls around the bearing while rotating at a given speed. The general view is that oil whirl frequency varies between 40 to 50% of shaft speed. Oil whirl may not occur in tilted pad, pressure dam, and crush fit bearings. This writer agrees with these generally held views. However, additional information can be learned from the time domain signal and frequency domain spectrum. Figure 19 contains the time signal and frequency spectrum from an oil whirl problem. Turbine speed is 93 Hz, and oil whirl frequency is 43 Hz. In most machines that have oil whirl problems, a knocking noise can be heard. This noise is generated because the oil whirl does not occur continually. Rather, the shaft makes a few whirls, stops for a couple of revolutions, then makes a few more whirls. This intermittent whirling can sound like a knock. The time period between points 1 and 2 in figure 19 is 0.02325 seconds or 43 Hz, which is oil whirl. The time period between points 3 and 4 is 0.01075 seconds or 93 Hz, which is turbine speed. The time period between points 5 and 6 is 0.1428 seconds or 7 Hz. This is the frequency of maximum oil whirl amplitude. There is a spectral line at 50 Hz, which is 43 Hz plus 7 Hz. There is also a spectral line at 36 Hz, which is 43 Hz minus 7 Hz. The spectral line at turbine speed has plus and minus sidebands of 7 Hz, which are 100 Hz and 86 Hz. A spectral line is also located at 136 Hz or 43 Hz plus 93 Hz, which is the sum of oil whirl frequency and turbine speed. This frequency also has plus and minus sidebands of 7 Hz or 129 Hz and 143 Hz. Note: the spectral line at 50 Hz is a sideband or some frequency and is higher in amplitude than the discrete frequency at 43 Hz. A sideband cannot be higher than the discrete frequency, except when the sideband equals a resonant frequency or contains more energy than the discrete frequency. From the above empirical data, it would appear that oil whirl frequency is equal to turbine speed minus 7 divided by 2, or oil whirl frequency equal to speed turbine minus 7 divided by 2 equal to 93 minus 7 divided by 2 equal to 43. This formula meets the current description that oil whirl is somewhere between 40 and 50% of turbine speed. We recognize that some refinements to the formula may be required in the future. Thank you.